What is color? Where does it come from? For us, living in a world saturated with vibrant hues on high-definition screens, the answer feels simple, almost intuitive. But for most of human history, this was one of nature's most profound mysteries. The answer to this ancient question was unlocked not in a grand laboratory, but in a darkened room, by a quiet and intensely focused mind. The man was Isaac Newton. And a simple, beautiful phenomenon, a beam of sunlight sliced into a rainbow, was his key. He didn't just see a rainbow, he saw the truth. He would use this to dismantle over 2000 years of scientific dogma and write an entirely new chapter in our understanding of the universe. This is the story of a man who invoked the rainbow, and in doing so, revealed the true nature of light itself. Part 1. The World in Darkness. Light before Newton. To truly appreciate the seismic shift Newton caused, we first need to understand what the world believed about light before him. For centuries, the giant of scientific thought was the ancient Greek philosopher, Aristotle. Aristotle's theory, which held sway for nearly 2 millennia, was that color was a product of mixing light and darkness in different proportions. A red sunset, for instance, was thought to be the result of a certain amount of darkness mixing with the sun's pure white light. White light was fundamental, absolute, and pure. Color was a modification, a stain, or a corruption of that purity. When it came to prisms, the explanation was simple: the glass itself somehow tainted the pure white light. The prism was adding the colors, like a painter's brush. The different angles and thickness of the glass were thought to create the different colors. It made a certain kind of sense. After all, if you passed white light through a blue piece of glass, the light came out blue. Why wouldn't a prism work in a similar, but more complex, way? Even great minds of the early scientific revolution, like René Descartes, subscribed to variations of this idea, suggesting that light particles spun at different speeds to create color. But the core assumption remained: white light was primary, and colors were created by its interaction with objects. This was the world Isaac Newton inhabited. A world where light was pure, and color was an impurity. But Newton wasn't one to accept dogma without proof. He had a revolutionary new tool at his disposal, the scientific method. And he was about to use it to put the nature of light on trial. Part 2. The scene of the crime: Newton's darkened room. The year is 1666. While England is ravaged by the Great Plague, forcing Cambridge University to close, a 24-year-old Isaac Newton returns to his family home at Woolsthorpe Manor. This period of forced isolation would become his annus mirabilis, his year of wonders. It was here he would lay the foundations for his work on gravity, calculus, and, most dazzlingly, on optics. Newton had become fascinated with light and the way telescopes of the day produced images with blurry, colored edges, an effect called chromatic aberration. He suspected the problem wasn't just in the shape of the lenses, but in the very nature of light itself. So, he began a series of now legendary experiments. He sealed his room in complete darkness, save for a single, small hole he drilled in his window shutter. This produced a precise, manageable beam of sunlight. His primary tool was a simple triangular glass prism, which he had bought at a local fair. Just as others had done for centuries, he placed the prism in the path of the sunbeam. And just as expected, the prism worked its magic. It bent the light, a process called refraction, and cast a stunning, elongated band of colors on the wall. From top to bottom, the colors appeared in a consistent order: red, orange, yellow, green, blue, indigo, and violet. Just like a rainbow. Now, according to the prevailing theories of Aristotle and Descartes, the prism had manufactured these colors. The thicker part of the prism created the reds and yellows, while the thinner edge created the blues and violets. The prism had modified the pure, simple white light. But Newton noticed something that didn't quite fit. The shape of the spectrum on the wall was an elongated rectangle, an oblong. If the prism was just bending the circular sunbeam, shouldn't the resulting shape be a circle, perhaps a bit blurred, but still a circle? Why was it stretched out into this long band of colors? This simple question, why the oblong shape, was the spark that ignited a revolution. Newton began to suspect that the old theories were wrong. He hypothesized that perhaps the colors weren't being created by the prism at all. Perhaps they were already there, hidden within the white light all along. Part 3. The Experimentum Crucis. The crucial experiment. Newton devised an ingenious and decisive experiment to test his new hypothesis. He called it the experimentum crucis, Latin for the crucial experiment. It's one of the most elegant and important experiments in all of science, and it worked like this. Step 1. Isolate a single color first. He repeated the initial experiment. He took his single beam of sunlight, passed it through a prism, and created the spectrum on a screen or board. But this time, he placed a second board behind the first. This second board also had a small slit in it, allowing only a very narrow portion of the spectrum to pass through. By moving this slit, he could effectively select and isolate a single, specific color. Let's say he positioned it to allow only the green light to pass. Now, he had a pure beam of what appeared to be green light. The big question was, what would happen if he passed this single color beam through a second prism? Step 2. The unchanging color. According to the old modification theory, this second prism should have further stained or changed the green light. It should have produced other colors, just as the first one did with white light. But that's not what happened. The green light that came out of the second prism was still green. It was refracted, bent, by the second prism, but it did not split into any other colors. It remained stubbornly, purely green. Newton then meticulously repeated this for every color in the spectrum. He isolated the red light and passed it through the second prism. It came out only as red. He tried it with blue light. It came out only as blue. And so on for every color. This was a stunning revelation. These individual colors were pure, or homogeneal, as Newton called them. They were fundamental entities that could not be broken down any further by a prism. The prism didn't create the green light, it merely revealed the green light that was already part of the original sunbeam. He also noted that the red light was bent the least by the prism, while the violet light was bent the most. This explained the elongated shape of the spectrum. The white light wasn't bent as a single unit, its different colored components were each bent at a slightly different angle, fanning them out into the rainbow we see. This spreading of light into its constituent colors is what we now call dispersion. Step 3. Putting the rainbow back together. Newton, being the thorough scientist he was, knew he needed one final piece of proof. If white light was indeed a mixture of all these colors, then he should be able to recombine them and get white light back. He devised several ways to do this. One clever method was to use a large lens to collect the fanned-out spectrum and refocus it onto a single point. And when he did this, the colors vanished, and at the point of convergence, a spot of pure, brilliant white light reappeared. In another, perhaps more famous version of the experiment, he used a second prism, but this time he flipped it upside down and placed it in the path of the dispersed spectrum. The first prism fanned the colors out. The second, inverted prism did the exact opposite. It took the separated colors and bent them back together, recombining them. And the beam of light that emerged from this second prism? It was a single beam of white light. He had successfully unraveled the rainbow, and then woven it back together again. Part 4. A new theory of light and color. The evidence was overwhelming, the conclusion inescapable. The experimentum crucis had shattered the old worldview. Newton's findings can be summarized in a few revolutionary points. White light is not simple or pure. It is, in fact, a complex mixture, a combination of all the colors of the visible spectrum. Newton called it a heterogeneous mixture of differently refrangible rays. A prism does not create or stain light. A prism is a sorting machine. It separates the colors that are already present in white light by bending each color at a slightly different angle. Color is an intrinsic property of light. The color of an object, therefore, is not a property of the object itself, but rather of the light it reflects. A red apple appears red because its surface absorbs most of the colors in the white light hitting it, but it specifically reflects the red light back to our eyes. If you were to shine only pure blue light on a red apple in a dark room, it would appear nearly black. This was a radical re-envisioning of our world. For the first time, there was a scientific, physical explanation for color. It wasn't magic, it wasn't a philosophical concept of mixing light and dark, it was physics. In 1704, after decades of refining his work and partly to avoid the fierce debates he knew would follow, Newton finally published his masterpiece on the subject, Optics, or A Treatise of the Reflections, Refractions, Inflections and Colors of Light. Unlike his other great work, the Principia, which was written in dense Latin, Newton wrote Optics in English. He laid out his experiments, his data, and his conclusions in clear, methodical prose so that others could replicate his findings. It became one of the most influential books in the history of science, setting the agenda for research in optics for over a century. Of course, it wasn't without controversy. Figures like Robert Hooke, a brilliant scientist in his own right, clung to the older wave-like theories of light and fiercely debated Newton. Newton, who famously hated public disputes, largely retreated from the debate, confident that the experimental evidence would eventually speak for itself. And it did. Part 5. The Legacy of Newton's Prism. The impact of Newton's work on light in optics is almost impossible to overstate. It echoes through our modern world in countless ways. That principle of dispersion, of splitting light into a spectrum, is the foundation of spectroscopy. Astronomers use it to determine the chemical composition, temperature, and motion of distant stars and galaxies. By analyzing the barcodes of light they emit or absorb, we can understand the universe without ever leaving Earth. The very technology you are using to watch this video is a direct descendant of Newton's discovery. Your screen creates a universe of color by mixing just 3 primary colors of light, red, green, and blue, in different intensities, a direct application of the principle that different combinations of colored light produce new perceptual colors. His work also led to practical improvements in the tools of science, particularly telescopes. By understanding that chromatic aberration was caused by the different bending of different colors, he was inspired to invent a completely new type of telescope, the reflecting telescope, which used mirrors instead of lenses to avoid the problem altogether. This design is the basis for most major astronomical observatories today, including the Hubble and James Webb Space Telescopes. It's true that Newton's picture wasn't entirely complete. He staunchly believed that light was a stream of particles, which he called corpuscles. We now understand, thanks to the work of scientists like Thomas Young and Albert Einstein, that light has a bizarre and fascinating dual nature. It behaves as both a particle, a photon, and a wave. But this doesn't diminish his achievement. His fundamental discovery, that white light is a composite of all the colors of the rainbow, and that prisms merely sort them, remains a cornerstone of modern physics. So the next time you see a rainbow shimmering in the sky after a storm, or the glint of color from a beveled piece of glass, remember the quiet room in Woolsthorpe Manor. Remember the single beam of sunlight, the simple prism, and the curious mind of Isaac Newton. He taught us that to see the truth, sometimes you first have to shut out the world, focus on a single beam of light, and have the genius to ask the right questions. He showed us that the rainbow was not a fleeting, magical apparition in the sky, but was, in fact, hidden in every single sunbeam, just waiting to be revealed. He didn't just unravel a rainbow, he illuminated our world.